So just to remind you guys, what's happening a week from today?
We have
Test.
Test, cool. So I've got the practice test for you. I'll pass that out in a couple minutes. I'll let more people come on in. That means that this Thursday is going to be review day. So every day before a test, that day will just be review. There will be nothing new on Thursday. The test is going to cover everything through what we covered today. So today we should finish out chapter 3. So we'll cover through chapter 1, 2, and 3 on this first test. Cool. So chapter 1, 2, and 3 homework. All of it will be due next Tuesday. So a week from today. Cool. Anytime between now and then, by the way. Feel free to turn in earlier. Any questions from homework? Yes.
Not specifically, but when we find that S value for the standard deviation, before that you have to square root that number that you get. What is that S squared number?
Yeah, what is that S squared number?
That's like, the book calls it the variance.
Yeah,
exactly.
It's usually like a really big number.
This is the population variance. This is the sample variance. And for right now, and in fact, it's only in some interesting mathematical applications that this becomes really important. Let me see. I can't remember if I said this. The mean, remember I said the mean kind of won the battle to be the measure of center? Remember that? Because when I take samples, the means of those samples tend to come together to be the real mean of the population. But if I take a median of samples, that's not going to come out to be the median of the whole population. You kind of with me? The variance, actually, if I took a sample and found its variance, those variances would actually target this better than the standard deviation itself would. We call the standard deviation biased estimator, and this would be a non-biased, the variance. What does that really mean physically? Not a damn thing. I mean, that's a very mathematical concept. It's going to become more important when we get to, if we get to chi-square stuff way at the end of the semester. For right now, this is a middleman for us. Okay? Right now, this is, I haven't taken a square root yet. But this is called the variance. Cool.
We can tell you anything though?
No, not physically, no. Mathematically, it works better. This does than the standard deviation does. When I'm trying to do samples from a large population, it targets the real variance better. But for what we need to do, that doesn't really have anything to do with us yet. Yeah. Okay. That's a good question, though. And remember, the Greek symbols are normally population. Our symbols are sample. Okay. So any other questions from homework, general or specific? I'm an optimistic fool, I am. So I'm hoping that means the homework is doing really well. Some of you guys got homework back, you have corrections to do. When are the corrections for homework due? Which test? The final exam. Because one reason I do that is because there's going to be homework you turn in on the day of the test. If I make corrections due the day of the test, that's a little evil. Right? You'd have to quickly, oh shit. Right? So it's due the day of the final for two reasons. One, for that, and two, because I'd rather you keep up with new homework than get bogged down trying to correct old homework. Right? Final's cumulative anyway. If you do it way later in the semester, it's going to help you get ready for the final. So at some point, I want you to do those. Yeah?
What corrections for the quiz?
Good. Quiz and test corrections due by the day of the test. I like it. Yes, ma'am.
So, like on the test, would you be like testing us something that we haven't covered, like on quizzes? Because our quizzes don't cover everything from our homework.
Exactly. So the test is not going to be made only from stuff in the quizzes. It will be stuff from the homework. Yes. Cool. If you understand the concepts on this practice test I'm going to give out, and you're okay with the work that I gave you in the homework, you should be fine with the test. I'm not going to give you anything that's different from the homework. There's no need to do that. Cool. Okay. All right. So like I said, an optimistic fool, so I'm just going to keep going. Last time we did do an example of how to find variance and standard deviation. I want to do a quick example of that again, and then I want to show you a different formula for it that's quicker to do calculation-wise. The formula we have right now for the population variance is this here. So one thing I need to fill in from last time, is what about the sample variance? Is there a difference besides, here I put a little n, so I'm just going to use a little n, but there's a huge difference between population variance and sample variance. And it's not just the letter. So for the sample, I'm going to use our letters. The difference is this. Now let me see if you guys can follow me. And the difference is going to be, calculation-wise, is going to be really easy. But I'm going to try to explain a little bit about the concept. So right now, there's an average age of everybody in the room, right? And it's just changed. So now there's an average age of everybody in the room. If I took a sample of you guys and took the average age, will it be the same as the average age of everybody in the room? It could be, but I'm going to put my money on it not being the same, right? Yeah. I could arbitrarily, randomly pick a bunch of younger people or a bunch of older people. You with me? Now think about this. I really want you to think about this. What does the standard deviation tell us? What does the standard deviation tell us?
However, our value is closest to the true value.
Sort of?
How much the values vary between each other? Or from the median?
From the
median?
Mean. Cool. Right? So it gives me an average distance from the mean to each data point. So it tells me how much on average do the values differ from the middle. And if you think about it, doesn't that just make sense to be the spread? The more that they are different from the middle in general, that means it's going to be more spread out, right? So if my standard deviation tells me how far my data values are away from the mean, right? You with me? And let's say the real mean of the ages in this room, let's say it's 20.9. You with me? Nothing major yet. And then I take a sample. Let's say I take a sample of 11 people and I get an average age of 19.1. When I calculate the standard deviation for this sample, I can't put this in there, can I? Because I don't necessarily know that, do I? So one thing that's going to change in this formula is I can't put that there. What do I have to put there instead?
X bar.
X bar. So that's one thing that's going to change. Now, I desperately hope that some of you guys understand what I'm about to say. If you don't understand it, you can still do the work. But it'd be so cool if you understood why this works. So if I took, let's say I take these two rows. I don't know if there's 11 of you. Let's just pretend there is. 3, 6, almost. All right, I'll include me. There. So if I take these two rows and me, the average age of these rows and me is this, right? What's going to be true probably about the people in these two rows? Which one are they going to be closer to? The real mean or this average from the sample? This came from these two rows. So they're probably going to be closer to that mean of these two rows, right? So the real variance of the population is related to the real mean. My sample standard deviation is always going to be a little bit less than it should be. Because when I change my sample, it's going to be a different mean. Everybody's going to be closer to that mean than they would be to this. So all those distances are going to be a little bit smaller than they really should be. So really one way to say that is sample means follow the samples. If I take one sample, there's a sample mean. You guys kind of cluster around that sample mean. Take another sample, it's a different mean. They cluster around that sample mean. Those standard deviations would be smaller than they should be. How are we doing so far? And again, if you don't quite follow me, it's not the end of the world. So how do I correct for that? This is actually just an adjustment. Instead of dividing by this number, if I know my answer, if I put this, if I know it's going to be too small,
gonna be n minus 1? Yeah, yep.
I could divide by something smaller. If I divide by less, don't I get bigger?
Yep.
Yeah. Now, I can't fully explain why it's exactly n minus 1, but I can at least give you a clue. Remember the other day we talked about degrees of freedom? Remember that? Degrees of freedom? And the degrees of freedom was 1 less than the sample size. So mathematically, it actually has a bit to do with that idea. So on one level, I want you guys to realize this is just an adjustment because it's a sample. Not the whole population. If my population is billions of people, and I take thousands of people in my sample, how big of a difference would n minus 1 really be? Not. Right? So in that level, it really doesn't make that big of a difference. Okay. Maybe. So what do you take from that if you didn't quite understand the whole means following the samples talk I did earlier? You just take from that, I'm going to write these 2 formulas on my formula sheet.
Yeah.
And at the very least, understand why this is n minus 1. It's just an adjustment. Because it's a sample, it's not going to be quite right. This is the best way to adjust it. Cool. So everything we did last time still applies. But if I tell you it's a sample, if there's 5 data points, you don't divide by 5, you divide by 4. Right? 1 less than the sample size. So calculation-wise, this is silly. This is, okay, big deal. Right? Mm-hmm. So let's try one more example. We'll do it up on the calculator too. Of course, I always put my notes right behind the screen. Everybody got that? All right. How you doing there? You doing all right? Okay. You want to. Okay. Let's see. So let's make up some data. Let's say. Okay. I'm going to do this 2 different ways. So that's 4.3 forever. Is that, can somebody get the average? Is that 4.3 forever?
.3.
Okay. Yep. So go ahead and put this data into your list. You can do that before this comes up. Go in there and clear your lists out. Several of you should have stuff in your list 1, 2, 3. Okay, cool. Did you guys see that okay, or is it too washed out? Can you flip the whiteboard thing in? Thank you. That's a little better. You guys really don't want me to know anything. 3. Okay. So to do the formula that we have, and the formula that we have, oops, I'm going to tell you this is a sample. So I want to use this here formula for the variance. All right. That formula there. There's the data. Cool. Okay. Oh, you know, better. So who remembers what we do next to kind of fill in that table? What's the next column have to be? exactly, the difference from the mean. Let me put it here. There you go, that's better. Okay. Cool. And we just figure out the mean, and if the mean comes out to be something kind of disgusting like 4.3 forever, the calculator, don't round it to 4. Don't even round it to 4.3. Go ahead and put in there. Now, what am I going to put in here? The next column has got to be that how far each of these is from the mean. So what do I actually want to put in there? This is L1. So here I want to put L1 minus 4.333. Put a few 3's in there. Make it a little bit closer. So put in there L2 equals L1 minus 4.333. Cool. There's that. So that's how far away, and the negative shows me if it's below, the positive shows me if it's above. That's how far away the data points are. And then what do I want L3 to be? Exactly. We just want to square L2. L2 squared. So I want L3 to equal L2 squared. Got to square that so I can get rid of those negatives so it doesn't add up to be 0. And we talked about actually value as a possibility, but it's too ugly mathematically. It's got that quick kink in it. So we use a square to make it nice and smooth. On a test or on your homework, this is what you would just copy down into your tables, right? I've got to see that, and you only have to do that up to chapter 1, up to the first test. After the first test, you never have to do this again for standard deviation. How do I get the, what's the next thing that I want? The formula requires me to do what? To add these up, right? So I want to add up L3. I want to add these up. How do I add them up quickly? Where do I go to add them up? So first do this, second quit. Get out of the list. Because anything you do right now, it's going to try to put into your list. You don't want to put the sum into the list. That'll freak it out. You want to get the hell out of the list. And then go ahead, sorry. Stat. So it's actually second stat. Good. Math. And then sum. I want to sum these up. You want to sum up what? So let me do that again. Go to second stat, math, and you can see all this other stuff you could do, right? In fact, look at number 7. That's very tempting. Sum up what now? L3? Oh yeah. Because L3 is what's got my x minus x bar squared. And that's what the formula is, sum those up. So we get this. So what do I want to do with that number now? Looking at my formula. Divided by. So this whole thing, I really want to stress this. I know in algebra you get so used to plugging stuff in. This is a little different. This is not a plug and shove formula. This is there are several values for this. I want you to add them up. We just did. Don't plug that number somewhere. This whole thing is that number. 0.3, whatever the hell it was. Divided by 5, good. 6 minus 1 is 5. So let me show you a nice thing here. If you just hit the divided by button. Can you remember if I said this about A and S, the answer key? That's temporary memory as the last number that showed up on the screen. That is a very cool little built-in memory button. Because now I can just divide, I don't have to type the whole damn thing over again. I just say divided by 5. And what's that number?
9.467.
Okay, that's what the number is, but what's it represent?
Variance.
Cool. Blah, blah, blah. So how do we get the standard deviation? Take the square root. So on the calculator you would hit square root. I don't want to type all that crap in, so let me just say square root of answer, ANS, right above the negative button. ANS always holds the last number that was on the screen. So there it is. 3 point, what would you say? 3 point, careful, 077. Always go at least 3 spots. How are we doing there? Doing okay? So if you want to go more, I'm all for that. Just don't go 16. Don't go crazy. 3 is normally good enough round to not throw off the answers you get when you use the standard deviation in formulas, like we're going to do pretty soon. It's not going to throw it off so much. If you round to 2 places or 1 place, it's going to throw your answer off by more than you expect. Okay. So let me show you the other formula. I gotta get 2 cameras. All right, that'll work. Cool. And don't worry, I'm gonna show you a little bit of the math. You're actually gonna help me with it. But you can have an entire semester class. Some of you guys know this. You can actually focus on the math of this thing. We're not going to. I'm just going to show you a little bit of why this leads to what it does. If I saw this in algebra, what do you think I should do with that? What does your gut tell you you should do with that? You know, if I saw x plus 2 squared.
Yeah,
it's already factored. So what do you really mean? You mean FOIL it out, right? You mean unfactor, right? Multiply it back down. So if I did that, what would I get?
X squared minus x bar.
So it's actually minus 2 of those, right? Is that cool?
Yeah.
Minus 1 minus another one plus x bar squared. X bar is sum of x over n, right? Remember that? The mean is the sum of them divided by how many there are, of course. So I could throw that in there and start messing with it. After you do all that math, this is the math I'm going to skip. You actually end up with this. Now, of course, the first thing people say is, holy shit, that does not look easier in any way, Jeff. Notice how many columns I need and how quickly this is. Is the mean anywhere in this formula? So one thing is I really don't need the mean to calculate the standard deviation now, right? And real quick, do you see how this comes out? See how this first thing would be sum of x squared? Do you see it right there?
Yeah.
And this comes from these x bars being replaced with sum of x over n, and they reduce down. You start putting all the terms together and do all this stuff. You end up here. Right?
Is that a percentage error of this example?
No, it's not. Yeah. But notice this. I really just need to add up my x's and put that number here, and to add up my x squares and put that number there. That's all the formula needs from me. The formula looks a little bit uglier, but it needs less stuff from me. It's kind of nice. Here I could end up with ugly decimals. Here I'm not going to unless my data is decimals, right? So in this case, for these numbers, we already figured out the mean by hand. What they add up to be? 26, right?
Yeah.
So to do this formula, you would say 26 is there, right? Sum of x, the sum of the x's is 26. What's the sum of the x squares? We'll have to square them to see, right? And I'm going to let you guys, you can use whichever formula you want to. I really don't care. This one I call a concept formula. This one I call a calculation formula. I can see the idea here. Add them up divided by how many there are is the distance, the average distance. Here I kind of lost that idea, but it's a little easier to do calculation-wise. So if I wanted to, in L2, I could say square L1. And there's my squares. And if I add those up, I get 90, 140, 160. 20, 70, yeah, 160. Cool. So the sum of x squares is 160 minus the sum of x is 26. Square that, divided by n. There's 6 things. Divided by n minus 1. 5 things. So I really just need 2 columns. I don't really need the mean in this formula. It's a little bit quicker calculation-wise. You can use whichever formula you want to, though. The book does this one more often. Even this one in the book, they do this in a different format that I don't like. So I want to show you this format. You can choose whichever one you want. And let's see if we get the same answer. $160 minus 26 squared divided by 6, and then divide that whole thing by 5. Yeah, that already looks familiar, doesn't it? There's that, and then square root that. There it is. Why do you think it's a little bit different? See how it's a little bit different from what we got earlier? It's a little bit different at the end. Why do you think that is? What did we use for the mean? Yeah, and we didn't repeat it forever, did we? We just doing 3, 3, 3. So it's going to be a little different way at the end here. You guys see that? That's why it's a little different. This formula doesn't need the mean. It's not going to have that same rounding problem. Okay, maybe. So, just to remind you, who remembers how to get to the standard deviation quick? How do you calculate stuff to do with your data?
Stat.
Good. So hit stat.
Calc.
Calc.
One var stat.
One var stats. I love it. So we only have one variable here. So if you hit one variable stats, it defaults to list 1. If you had some other list, you can put in there list 2, but I don't want list 2, I want list 1. And sure enough, which one of these do I want? This is where you have to be careful. The calculator only sees a bunch of data that you put in. Does the calculator know if it's a population or a standard or a sample?
No.
No. So it gives you both. It says you choose, man. I don't know. We know it's a sample. We take this one. This doesn't mean if you don't want this, you can pick this. I don't want. I want this. No. It depends on is it a sample or is it a population. Cool. Okay. Let's see. Let me let you guys try one out real quick on your own. You can use either formula that you want to. So I want you to find the standard deviation for this. It's a sample. The only thing you can't do at the moment is do one var stats and stop. You need to see the work.
Is there a way to clear all lists at once?
There's a,
Individually.
if you hit stat, there's a, you have to still do it individually. See number 4, clear list?
Yeah, but it doesn't.
But then you have to list L1, comma L2, comma L3.
Oh.
There's no clear all list. You can memory reset, but that does a lot more than what you want it to do. come out nice for the mean, just so that wouldn't trip us up.
Okay.
You're welcome.
Also came pretty good for the
Standard deviation came out good?
for their S squared came out pretty good as well.
Cool. I can't take credit. Let me know if you're having technical difficulties or conceptual issues or anything.
It is, see this plus this, is that plus that.
Oh, there you go. I meant that. Oh yeah.
Of course you did.
12, 15. I'm trying to remember the Pythagorean triplets. 3, 4, 5.
Yeah. We were doing it yesterday, weren't we? We were doing multiples of it as well.
Okay. Oh, you want L2 to be, which way are you going to do it? X minus X bar? Okay. So you want, so L1 is your X. So you have to know what X bar is. Then you can put L2 can make it equal to L1 minus X minus X bar. Because all your X's are in L1. No, go ahead and get to that. Okay. Because it just makes more sense to us. Like I say, right. Square root of 11. So yeah, statistics is more of an application of method. So that's why I don't need the exact answer. I want the approximate.
What'd you get?
I thought so. I got 19 for a variance.
Oh, so this was got the wall that we
Okay, one of us is alright.
One.
What the fuck happened here? Maybe I summoned it.
Oh, I know what I did.
You got an L3 to A. Yep. Alright, so that did. Oh, something's more up here. What was your number here? Why did you did? What was your
The long way is easier.
Yeah.
Because they added to the 50.
For variance or?
No, for the whole thing, the standard deviation. For variance, it's 60 points.
You got 60. How come I got fucking 8?
Oh, I'm sorry.
I did it 2 different ways. The calculator says it's 8.
What's that?
What is that?
One thing is because it's an adjustment because it's the sample of standard deviation is always going to be smaller than the true standard deviation of all populations. To make it a better approximation for that,
Did you get
divide
18?
by lower to make it a little more.
Some.
Okay, you know what you're doing over here?
That's
The
what
real
the
math
calculator
behind it is
says.
a little more complicated.
Yes, that's what it says.
That ends up
I got
being
that.
the best way to make
You get that too?
all the sample standard deviations target the population the best. Or the variance. if I left it at n, the sample standard deviation would be
What do you got for that?
not a good approximation of the true
These guys
standard
divided
deviation.
by their numbers.
Because each one is based on its own mean. Right?
X minus
So I've
X
got to
squared,
divide
yeah.
by a little less to make each one a little bigger. Because each one underestimates the standard
That's
deviation.
50
Looking at its
squared
own
divided
mean.
by 5.
Even though it underestimates, not overestimates.
2500 divided by
Well,
5
sometimes it
is
would
500.
overestimate.
Oh,
Most
no,
of the
no,
time
no,
it's going to
no.
underestimate.
Doing something
Because
wrong.
when I take a
Divided
sample,
wrong. Oh, no.
those
Oh, yeah,
sample
which-
data elements are going to be
Fine.
closer to their own mean. So they're each going to be closer to what they think is the middle. When the real middle is
Did you do
something
something
else.
different?
Yeah, I used
So when I
that
take
one.
all the
What did you
samples and
do?
try to average them together to
Yeah,
get what the real standard
it's
deviation is,
confusing.
it doesn't come out right unless I do this.
3, 10,
Just to
24,
adjust
11.
for the fact that it's a
Oh,
sample.
fuck, I just cleared the list.
What? 7 point what?
He got 7.8. You got 7.8?
Good.
And then go with this now so it's summation of the top, right? So the
Summation of
summation
the top. And then square what you get on the end.
So and then yeah, so that would be that would be the same. So that would be that.
That's adding these up.
Yeah, that's adding those.
Now when you add these up, this is you on the
Oh, you did it for the damn
That's all right. So all your work is
7, 8, 7.8. That's the population.
Yeah, I
That's the
know.
right idea.
Would that be enough?
We're doing sample.
That's what.
I don't get it.
Showing me the numbers.
We're looking for sample variance. You did population
And you can
variance.
double check it with the
Well, I
one
can
more
get
step.
that too by just dividing
I
this
didn't
one
do
by
it this night.
Oh.
Because
We did something wrong.
that way.
Just take it out one more place. And then to check it, it's that.
I got
One
4.
more step, so it's 14. Enter, defaults to just one. Look at the sample variation. Yeah. All right, let me see. Let me catch up to you guys. The average comes out to be 10, right? They add it to be 50.
Yep.
Divide by 5 is 10. That's mighty nice. So L1 minus the average. That's what L2 is.
Okay.
That's the x minus x bar. Then I want to square them. Oops. Yeah, here. Square L2. That's my x minus x bar squared. Oops.
It's 8.8.
Make this thing too realistic. Hit second. There you go. And then what do I want to do with L3?
Sum it up.
Sum them up, right? That's my x minus x bar squares. I want to add those up. So if I get out of here, sum the L3, 310. I want to divide that by n minus 1, right? So divided by 4.
Okay.
And then what do I want to do with that thing? That's the what? What is that physically?
Variance.
That's the variance. Cool. That's before I've square rooted. So now I square root that. So I definitely suggest that you tell yourself what the hell it is you just got. Right? Put s squared equals 77.5 so you know you're not done. You still have to take a square root to get the s by itself. Cool. So hopefully everybody got this. If you did it the other way, then you would just make L1 the x's, L2 the L1 squared, and then sum both of them up and throw them into the formula. Right? So if you want to do it that way, you should end up with the same thing. To check this real quick, I hit stat, calc, 1 bar stats. It defaults to L1, so I don't have to put any list in. And also look real quick at the very top, it tells you the mean. So you can always do 1 bar stats to get the mean and then go do the table. And I know that some students say, well, you gotta do the table, I can see it. Because you gotta learn. You can't just get the calculator to tell you all the answers. But that's a really good place to check your answer question. 8.803, I love it. Okay. So any questions about that?
Can you go over how to do the
Oh, sure. Notice something else about this. It gives you the sum of x, and it gives you the sum of x squared. Now, don't think you can just put those down. You still have to make the table. But the table's pretty easy to make. Go to stat, edit. For my L2, I've already got my x's in L1. I want my L2 to be x squared. So L1 squared. So there's the squares. And how do I sum that list up? I need the sum of my x squares. I just go to stat, calc, one var stats, oh I'm sorry, list, and I have
Got it? Yeah.
number 5, and then I can sum up L2.
Variance, that's what it's fucking.
And look here, there's the sum of my x squares, 810. So on the one hand, I want you to realize, students get upset because it gives you the answer. Why have to do all this other work to get the answer? Because you got to see what goes into it. This is part of learning. But the other nice thing is, I can check every damn thing I get. I can check to make sure I'm on the right track. Can you do that in other classes? No. So appreciate that. Later, when we get out of chapter 3 after this first test, we're going to be getting the standard deviation directly from here, because then we got a lot of other stuff to do. So I'm not going to waste time just making the table. We can all do that after chapter 3. Okay. So is that cool? So then to put it into the formula, it would be the sum of x squared minus the sum of x's squared divided by n, and then all that divided by n minus 1. And that looks pretty familiar. That's what we get the other way too. Pick the square root of that and you're good to go. So you can pick which one you want to do, which formula you want to use. So a couple last things in section 3.3. So what you'll notice for this class, just to let you know, each time we hit a different situation, a different way for somebody to give me data, because there's more ways than just listing a bunch of data. If they just list a bunch of data, I do what we just did. They can give it to me in a lot of different formats. But we're going to continuously want to find 2 things. The quickest 2 things to get to describe my data is the mean and the standard deviation, because it tells me where's it centered and how far from that center does it get on average. Those are the 2 quickest things to tell me, and I get a feel for what the data looks like without you actually having to show me. You know, billions of pieces of data, just tell me the mean and the standard deviation, and I'm good to go. So the last thing in here is a little bit conceptual. There's 2 pieces to this, actually. This is the first one. Right, Chevy-Chev's theorem, or I call him Chubby Dude sometimes. I have no idea if he was chubby, actually. But it just came out my mouth one day, so now I call him Chubby Dude. Here's the setup, and I'm going to use the same setup for a couple different ideas in this class, because I think it makes physical sense. If I went somewhere, I don't want to be specific because it can't be wrong. So let's say that there's a little island somewhere. And I go there and I start talking to the people and I ask them, how old are you? And then I plot that age. So this is like just born, and this is like, 120. So I start putting little dots. So I make sort of like a dot plot. But at the end, I'm talking to like a lot of people. There's thousands of people on this island. So I end up with a picture that looks like this. So that's a graph of their ages. What's a very strange thing about that graph?
There's no middle age. Nothing.
Nobody in the middle, right? So that could talk about something weird that happened in their history. Who knows? But all we know is that's what it looks like. So I got a bunch of really young people and a bunch of older people, but nobody in the middle really.
Is that so? It's not.
Yeah, is this a bell curve?
No.
It is sort of symmetric, but it definitely doesn't go up and then down. It goes up and down and then up and then down. That's not a bell curve. Yeah. Cool. Where would the mean be?
In the middle or something.
Yeah, somewhere in here. Right? In fact, let's say this is a population, so that's a mu. Okay, so this is obviously not a bell curve. I'm kind of glad you brought that up. Because when it is a bell curve, I could be a lot more specific. Because it has to follow a certain format. Here, this is just some weird distribution. Who knows what the hell's going on? The standard deviation here,
No one was born for a while.
yeah, for some reason,
They went to
nobody was
war.
born, or all these people died. Like they have everybody fighting their army, and the whole army was wiped out, and they were all this age. I don't know. I'm not sure what happened there. But let's say the standard deviation is like this. So if I go one standard deviation up and one standard deviation down. Let me just stop right there and let you kind of absorb the symbols I've used. Right? This is the mean plus a standard deviation up and the mean minus a standard deviation down. Let's give some numbers to maybe help us out here. Let's say the average age was 41. And let's say the standard deviation is, let's say, I don't know, Jeff, 4. So what would this age here be? 45. And this age would be 37. How we doing? Doing okay? Okay, nothing too freaky yet. Very often what I'm going to say when I mean standard deviation is I'm going to say step. Because how many steps have I taken up from the mean? I've taken one step. Where each step is this big. And it kind of makes sense. If my data is really skinny like this, and I take too big of a step, I miss the whole thing. It's sort of like driving along one of those roads and you blink and you miss the town, right? Have you ever gone through one of those towns? Blink. If I take too big of a step, I'm going to pass the whole damn data. The standard deviation here would be really small, right? So to see the data, I would take little tiny steps to see the whole freaking data. So that's why I'm going to call standard deviation steps. Kind of makes sense. I'm stepping around my data.
So one step is always one standard deviation.
Exactly. And when I say step, that's what I mean. I mean one standard deviation. Okay. So of course I could take, now how much data, if I do that, how much data did I actually just catch?
2 standard deviations.
How much data physically, in reality? And the data here is ages of people. How many ages did I just catch? None. So that could happen. So this guy's theorem, it says within one standard deviation of the mean, there's at least 0% of the data. Now that is really going out on a limb. Thanks a lot, dude. I couldn't figure that out on my own. There's at least nothing. Okay. So far, his theorem is a little lame. But here's where his theorem really gets interesting, and you're not going to think this at first, maybe. But if you take, and the way I've drawn my picture, of course, if I take one more step, I catch some data, don't I? And my picture's not to really scale very well, but oh well. This would be mu plus 2 steps, mu minus 2 steps, cool? So what age would this be?
33.
33?
49.
49? How are we doing? You guys see that? So if I give you a mean and I give you a standard deviation, you can start doing this, put the mean down, take a step up, a step down, another step down. You can develop that thing, right? That's pretty simple. So what he says here is within 2 standard deviations of the mean, there is at least 75% of the data. Of course, mine is not to scale very well, but hopefully you'll forgive me. No, maybe that's not true.
That's crazy.
Now think about that. Now if you're God and you don't like Chevy, you're like, let me screw with your whole theorem. I could reach down and do what to maybe escape the steps here? I'm saying I catch 75% of the data when I take 2 steps up and down. How could I try to escape that? Could I just take everybody, you're all older now. Screw you, God. You're all younger, some even up and born. So I could move this back and move this up, and then God says, screw you, chubby dude, you did not catch anybody. But what happens the minute I do that?
Change the standard deviation.
Standard deviation gets bigger. So then chubby dude said, haha, I stepped bigger, I still catch things, right? My standard deviation is now bigger. So of course we're not getting to the details of how he came up with this theorem, but we can at least understand the concept that why this theorem should work, no matter what. And this is the freaky part. You make any list of data that you want to, any list of data. You put negatives on there, you put 3 billion, you put 2, you get 0.01, whatever list of data you want, I'm going to calculate the average, the standard deviation, go out 2 steps. I'm going to catch at least 3/4 of all your numbers every single time. That is freaky. That is also useful as all hell. So if I had, for example, the average screw length somewhere is 0.7 inches, and the standard deviation is 0.1 inch, between what 2 values are you guaranteed that 75% of the screws fall in?
0.6 and 0.8.
So you could, this is what I was saying earlier, you can make this little thing here, right? 0.7. To find 75%, how many steps do you have to go? Twice, right? 2 steps. So 2 steps up, 0.9, 2 steps down, you can do it, Jeff, 0.5. So you'd say, is 75% of the screws, at least 75%, have to be between 1/2 inch and 0.9 inches. And I don't care what the data is, I don't care where it came from, I don't care what it represents. If you can get the mean and the standard deviation, you can say that. You can just take 2 steps up, 2 steps down, you say at least 75%. You with me? A little bit, okay.
We're going to see the math for this later?
No, we're not. Because actually, Chubby Dude, in this class, he applies to any distribution, like I keep saying. The one that we're going to focus on in this class is in what works for normal distributions, right? Because that's the one that really is useful in the extreme. This is somewhat useful, but the bad part about this one is that part. It could be 100%. Right? At any point, it could be 100%. We have no idea. It's at least this, at least this. And just to finish this out, within 3 steps, there's 89% of the data. Okay. So what this, for normal distributions, see this guy's probably, he's almost there. We have something called the Empirical Rule. And this is going to really, to tell you honestly, where this empirical rule comes from is going to actually be like 60% of this class. We're going to be using the idea that this comes from. This is a simplification of an idea we're going to get into later. This one sort of lists it like this. This one will give you a lot more specific, because for a normal distribution, it has to look something like this. It could be skinnier or fatter, but the minute I make it skinnier, my steps are smaller. If I make it fatter, my steps are bigger. And the fact that it must have the highest part in the middle, it must be bell-shaped, I can be a lot more specific with these. So what empirical rule says is, within 1 step of the mean. Let me do this. Let me see if I can get you guys started with this. If I call the mean 0, that's because it's 0 steps away. So this would be 1 step up, 1 step down, -1. Do you guys see that? Kind of preparing you for something later. So this would be the mean plus a step. This would be the mean minus a step. But the quick way to say it is 2 up, 2 down. Cool? Be somewhat. All right. I'll take that. So what this guy says, what the empirical rule says, is within 1 standard deviation of the mean. Can there be 0% now? No. Hell no, because it's supposed to be the biggest part in the middle. There should be most in the middle. And sure enough, within 1 standard deviation, there's 68%. And it's actually 68.26. But just to make it easy to remember, we're going to say 68%. There's no at least. There must be exactly 68.26, blah, blah. We're just going to call it 68. for everyday use. Is that all right? Okay, cool. Within 2 steps, within 2 standard deviations, there is 95% of the data. And within 3 steps, if I take one more step out, is there much of anything left?
Not really.
Theoretically, there's a little bit left out there. You just put -3 back there. If I take 3 steps up and down, I've now caught 99.7%. Okay. How are we doing so far? So there's only 0.3% outside of 3 standard deviations. We would definitely call those things outliers. In reality, anything outside of here we call an outlier. What's the probability? Oh shit, we haven't even talked about probability, but you guys can handle this. What are the chances that I find somebody who's outside of here?
1 in 20.
So this is 95% inside, so how much is outside? 5%. There's only a 5% chance. So we call anything outside of this, anything out here, up here, we call that unusual. I love that. Anything in here, it's not unusual. Anything out there, it is unusual specifically. So if something was 2.3 steps away, I would say that's an unusual score. It's outside of what I would expect. It's outside of what's normal. Yep.
Are we going to see calculations for that at least?
Eventually, yes.
How close to a normal distribution does that have to be for you to use that empirical formula?
That actually is at the heart of what we do. So that's an awesome question. A lot of the time we're saying, when am I allowed to use that? How normal is normal enough, right? So one thing that we do in this class, I have you guys doing a test, is you actually calculate what percentage of the data is in there. You just look at it and you see how much stuff is in there. And then I ask you, could that possibly be normal? Well, if it comes out to be 67%, you'd say, well, yeah, it's close. If it comes out to be 50, you're like, no, there's no way. You guys, so it's sort of loosely, sort of like just eyeballing something and saying, is that normal? That's roughly normal. Same kind of idea. Let me see. I think yeah, good. I want to give you a couple of specific examples of what you might see with this. Let's say this is normal. So let me see how far you can make it with this. My suggestion is draw the picture. Always draw the picture. So you know it's normal, you know what the mean is, you know what the standard deviation is. You can start doing like we did and start stepping up and down. While you guys are doing that, let me get out the practice test. I have an answer for this next time.